Hello, friends. Welcome to the session. In this session, we'll discuss about interrupts and priority management of interrupts. So let's begin. So interrupts are basically an events or signals that temporarily suspend the main program. So interrupts are the signals sent by the peripherals which suspends the executing program or a main program which is executing right now. When interrupt comes, if the interrupt has to be serviced, then before moving to that service routine, the value of program counter and program status word pc and psw are saved to the stack memory, and then control passes to interrupt service routine, that is called isr. So this is a program to be executed on interrupt. However, by default, PC and PSW will be pushed. If a programmer wants, he can use push operation to store other values. Then control goes to ISR and executes the ISR. Just while coming back from the ISR, again the content of program counter and PSW are retrieved back from the stack memory, which are stored during the interrupt. So if we have used any push operation to store the value, then similarly we have to use pop instructions to read the data back from the stack. Once we read the data, then control passes to the main program or which was previously executing from where it has left off. The push and pop operations together is termed as context switching, and time taken is termed as context switching time. Then coming to 8051, we have 5 interrupt signals. INT0, that's the external interrupt 0, then T0, timer 0 interrupt, then INT1, external interrupt 1, then T1, timer 1, then RI and TI, receive interrupt and transmit interrupt used for serial communication. Now, once we have interrupts, so we have to decide which interrupt is important and which is not. So for that, we have a priority management. So there is a interrupt priority register. If a low priority interrupt is executing, then high priority interrupt can preempt it or interrupt the lower priority interrupt. But if the two interrupts of different priority levels are received simultaneously, then request of the higher priority level is served first, and then the lower priority interrupt is served. Now, if the request of same priority levels are received simultaneously, then a default priority sequence is be maintained. That sequence is determined which request to be served. Now, to set the priority, we have interrupt priority register. Here we can see it's a 8-bit register. It's a bit addressable. We can access each bit independently. So first one, IP.0, it defines external interrupt 0. Whichever we want higher priority, that bit we have to set it to 1. Then that will have the higher priority. As usual, if we set more than one bit to the 1, then as we discussed, the default sequence is considered if both the requests come simultaneously. Otherwise, based on the priority, they will be executing. Now, bit number 1 is for timer 0, bit number 2 is for external interrupt 1, then bit 3 is for timer 1, and bit 4 is for serial interrupt. Then fifth and sixth bit are reserved for future use. Then we have to see what is a default priorities and what is interrupt vector table. Now all the 5 interrupts are vectored interrupts in 8051. That means for every interrupt there is a predefined address where the ISR should be written. Now if you remember, when we wrote a program for the various operations, we used to leave the first 48 location empty and then write our code. That is because from 003 to 23, these locations are reserved for interrupt. So after 30H, we used to write the program. Now, if you see here, external interrupt 0 is at 003 and timer counter for at 00B, that is the timer 0, then int 1, 013, timer 1, 1B, and serial port at 23. These are the addresses where the code has to be written. And remember, these addresses are of code memory. And above all this, we have one more interrupt called reset, which is a non-maskable interrupt, and that has highest priority. We cannot change that. These are five programmable interrupts, what we see here. Now, sorry. Again here, if you see the difference between the two addresses, we have very limited amount of memory to write the code. So what we can do is, at this particular address, we can use a jump instruction to go to some other memory location of the code memory, and then we can write the code there. That is, ISR can be written there. So this is how we have a interrupt vector table. Then we will see how to enable the register. Now to enable the interrupts, we have IE register, that is interrupt enable register. Again, we have 5 bits here used for enabling the interrupt, starting from external interrupt 0, timer 0, bit 1, bit 2, external interrupt 1, bit 3, timer interrupt 1, and bit 4 is for serial port interrupt. These 5 interrupt bits are used to enable the interrupts. Only when we set these bits to 1, only then that interrupt will be enabled for that particular peripheral. And to activate these interrupts, we have to first enable this all enable all bit, that is global interrupt bit, or enable all bit, we can say. So this bit should be made high. Only then these bits will have the effect on the programming. If this bit is 0, then all the status of these bits are ignored by the controller. Okay, thank you. Have a good day.